Okay, so this is 2022, paper 2, question 16, B and C. I'm doing this in school without my video editing set up at home, so I'm going to try a single take, so I apologise for the mistakes. Part B, show that every point on the curve satisfies that equation. This is converting parametric to Cartesian. And you may remember that there are two approaches. If it doesn't involve trig, if our parametric equations don't involve trig, we just rearrange one as t equals, substitute it into the other. If it does involve trig, as this one does, we've got to use one of our identities. Now, these parametric equations involve tan and sec squared, so I very quickly derived, I couldn't remember it, the identity that links tan squared and sec squared. We get that by starting with sine squared plus cos squared and dividing everything by cos squared. So tan squared plus 1 is sec squared. So what we do is we say, right, I can rearrange this equation as tan equals, and that means that tan squared is that squared, and I'm going to square it by squaring the top and squaring the bottom. And I can rearrange that as sec squared. So I can now rewrite this identity, replacing tan squared with that and sec squared with that. And it fairly quickly sort of falls out with what we were asked to do. So I started by doubling everything, which killed that fraction. So that became 2. And if you double a quarter, you get a half. And then I just added 3, and we got what was required. Okay, I then sketched that function, and I did it on my calculator, so there we go. Except, of course, in the question we're told that the range of values of t limits this curve, so it won't be the full curve, it'll start somewhere and it'll stop somewhere, but that's the shape of the curve. And in part C, we're asked to show, trying to find my solution to part C, sorry, this is probably a single take, there we go. We're told that this curve meets this straight line twice. And so what we're saying is, this is a sort of sketch of the parametric curve, although we know it starts and finishes somewhere, we'll come back to that in a minute. The line we're trying to prove that it crosses twice, I'm rewriting that like this. So it's a straight line with a gradient of -1/2, so it looks something like that. And depending on the value of k, that line will sort of slide up and down the axes. And I hope you can see, therefore, that the value of k needs to be bigger than this value here in order for the straight line to cross the curve twice. So the way we approach that is we just deal with it as a simultaneous equation problem. Both the Cartesian version of our parametric curve and the straight line that we're asked to work out the value of k for are written in y equals form, so I'm just going to make one equal to the other, and that gives me a quadratic equation. But actually I'm not going to solve that quadratic equation. All I need to do is work out what value of k gives this equation 2 solutions. So this is a discriminant problem. So I know that with this quadratic there will be 2 solutions if b squared minus 4ac is positive. And in this equation a is 1, b is -1, and c, the things that aren't x, is minus 2k. So I work out what b squared minus 4ac is. -1 squared is 1, minus 4 times a times c, making sure I know I've got minus minus, and that tells me that k has got to be greater than 43 over 8, so it's 5 and a bit. So what that shows me is that when we've got the line meeting the curve once, k must be equal to 43 over 8. So I now know that k's got to be bigger than 43 over 8. Is that the end of the problem? Well, first time I did this, I thought it was, but I'd missed something. Do you remember we said that for the parametric equation, we're told that t goes from minus pi over 4 to pi over 3. So what I did was I went all the way back to the original parametric equations and worked out the value of x and y I got when t was pi over 4, minus 1, 7. So that means the curve starts at minus 1, 7. And when t is pi over 3, you get this rather horrible number. And I'm just very quickly on my calculator typing in what 1 plus 2 root 3 is to get a rough idea. So it's 4.5-ish. So it's 4.46. Y is 11. So if I go back to my picture of a curve here, I know this curve goes from minus 1, 7, so that's perhaps here, all the way to 4.5, 11. So that might be up here somewhere. So actually the curve is only defined for these values here. It's not defined beyond that. And that means that there will come a point with this line here as it slides up. We already know that that's 43 over 8, but as k gets bigger and bigger and bigger, there'll come a point where it will pass that point and will therefore, like this one, only have one solution. So what we need to do is we need to work out what value of k makes it go through that point there, and therefore that's the biggest value of k that we can get. So we've already worked out the smallest value of k, because that's the value of k that goes from one solution to two solutions. We used the discriminant for that. Now we're just saying, when does the straight line, y equals minus a half x plus k, go through that point there? Because as soon as it's gone through that point there, we'll only have one solution. The straight line will only cross the curve once. So there we go. I did it for both points. I didn't need to do it for that point there, because my picture shows me that that's the only point. So at minus 1, 7, using that straight line, you get a value of k is 6.5, sorry. And so that means that k has to be between these two values. Remember, this value was the value of k that gave you one solution, so bigger than that it needs to be, but at that point it's still touching the curve twice. As soon as it gets bigger than that, it will only touch the first one, so it's allowed to be equal to that. Very happy to sit with you and go through this face to face if that's not clear. It's a really tricky question. Question 16 on a A-level pure paper tend to be tricky, and this was no exception. Well done.